This is a handheld NES. Wait, no, sorry. This is a handheld NES. And everything from the hardware to the software I built from scratch. This is my first ever embedded systems project, an NES emulator running on an ESP32 that runs at native speed with full audio emulation and save states implemented. At the time, I thought it would be a quick side project, but I could never have imagined how painstakingly difficult it would be to make and optimize an NES emulator for the ESP32. This is how I made it, and how you could easily make one as well for less than $20.
What will the future bring from Nintendo? More hits like Super Mario Brothers. Sports hits like Mike Tyson's Punch-Out! Nintendo has the most video game hits. Hogan's Alley, The Legend of Zelda, and more like Metroid, Rad Racer, and you can play them only on the Nintendo Entertainment System. Now you're playing with power.
Like most people, I got into the world of embedded systems through this little board, the Arduino Uno. I fiddled around with the Arduino Uno and programmed Blinky, the hello world of microcontrollers, but I never found any inspiration in making a project with it. Then, one day, I learned about the ESP32. Needless to say, this tiny little chip is amazing. Compared to the Arduino Uno, it features a dual-core or single-core 240 MHz processor, which is a whopping 15 times faster clock speed than the Arduino Uno, a standard 4 MB of flash, 520 KB of SRAM, supports Wi-Fi and Bluetooth, 34 general-purpose I/O pins, and the kicker? It costs the same as an Arduino Uno, if not less. When I first started with the Arduino Uno, I always had in the back of my head that I wanted to make an NES emulator, but the Uno was far too underpowered. Once I learned of the ESP32, I knew what I had to do. So, I bought an ESP32 development board. Before starting to program the emulator, I had to choose the hardware for the handheld. Choosing the hardware is pretty straightforward. A handheld needs a screen, speaker, a place to store the games, some buttons, and of course, a battery. After searching online, I decided to use these parts. I ordered the parts online, and once they arrived, I started testing each part individually, learning how to interface with them and avoiding debugging hell later on. Now that we have our hardware, it's time to start the software. Having already written an NES emulator for Windows, I thought it shouldn't take that long, right? And so begins the writing of the NES emulator and the painstaking months of optimization. You would think that the 240 MHz would be enough to emulate the NES, considering that the Intel i386 CPUs back in the day could emulate the NES with around 30 MHz. But as you'll see, that is not the case. So, how do we go from this to this? I implemented 5 big optimizations for the emulator. Let's go over them one by one. I start porting over my NES emulator on Windows, and instantly I know there's a problem. The frames generated by the emulator need to be stored in something called a frame buffer before being pushed to the screen. Unfortunately, at the NES's resolution of 256 by 240 pixels and 16-bit RGB, that would mean that the frame buffer would take 120 kilobytes just for the frame buffer. This would leave us very little memory left of the emulator and the game ROM. Luckily, this is an easy fix. Instead of storing a whole frame in a buffer, we can store only a few lines at a time in the buffer. This will free up a big chunk of memory for us. However, it will also incur a performance overhead. But this is a trade-off that we have to take. Another optimization we can use for the line buffer is the use of direct memory access, or DMA. DMA is a hardware mechanism that allows the transfer of data from RAM to a peripheral, in this case the screen, without any CPU involvement. This allows us to push the line buffer to the screen with a minuscule amount of CPU overhead. The biggest optimization I made was not rendering the NES the way that the real hardware does it. The original NES renders pixel by pixel. Every single pixel is processed one cycle at a time. But on a microcontroller like the ESP32, it's a performance nightmare. So instead, I switched to a scanline-based renderer. Rather than rendering pixel by pixel, I render an entire horizontal line of the screen in one go. This lets us batch the work done to emulate. Thus, the work per frame drops dramatically. And without that change, this emulator simply wouldn't run at full speed. This approach does sacrifice accuracy, but it's a necessary trade-off as the performance gain is massive. After that, I decided to implement more mappers. Now, what are mappers, you might be asking? The original NES console was designed to only address up to 64 kilobytes of memory, and only 40 kilobytes of the memory space was available for game data. Early games like Super Mario Bros. And Donkey Kong fit in this space easily, but as developers made more complex games, more space was needed. Later games in the NES's life, like Kirby's Adventure, used over 700 kilobytes, and the biggest game on the system was 1024 kilobytes, or 1 megabyte in size. That's a whopping 25 times more memory than what the NES can address. Take note of this. Instead of redesigning the whole console, Nintendo opted to put extra hardware chips inside the game cartridges. The NES uses these specialized chips inside game cartridges, called mappers, to act as memory managers. Essentially, mappers allowed the console to select a big block of data called banks to read from and switch banks whenever data from other banks is needed. This process is called bank switching. If you'd like to learn more about bank switching, take a look at my video about running Bad Apple on my own 8-bit CPU, where I go more into detail about bank switching there. Now, some of the sharp-witted among you might have realized a problem. How can we load and fit these over 500 kilobyte games in the ESP32's measly 320 kilobytes of RAM? The answer? We don't. Sort of. While we can't store the full game ROM inside of RAM, we can store the individual banks that these mappers select and switch to. Then, if a mapper does switch to the bank, we can dynamically load the data from the microSD card. So, I programmed some more mappers and a simple implementation of dynamic bank loading. And it's incredibly slow. Now, you would think that the games would only switch banks every few seconds or so, but when I logged and checked, they were switching numerous times per frame. Dynamically loading 16 kilobyte and 32 kilobyte chunks of data every few seconds should be fine, but several times per frame, that's definitely going to induce a huge slowdown. So, how do we fix this? Well, if we take a look at the amount of free memory that we have available, you can see that we still have a lot of unused memory left. We can take advantage of this extra memory and use a cache for our banks, a least recently used, or LRU cache to be specific. Essentially, we have a cache that stores a number of banks. If the mapper loads a bank, that bank will be loaded and stored in the cache. If the mapper loads another bank and that bank is already loaded and stored in the cache, then we won't need to load the data needed and we can read from the cache. Once the cache gets filled and the mapper tries to load another bank that isn't in the cache will remove the bank that has been used the least recently, hence least recently used cache. This ensures that banks that are used frequently remain in the cache. So I implemented an LRU cache for the banks, and the results are pretty incredible. Any kind of slowdown is gone. It's basically as if we aren't loading anything at all. At this point, I've implemented most of the important features of the emulator, except for one. The emulator is already emulating the CPU and the graphics renderer of the NES. But where's the audio? How will we hear the 8-bit music we all love and remember fondly? Currently, the emulator runs fairly, but now we have to add audio emulation on top of that. We aren't even at our goal of 60 FPS yet, and audio emulation is very performance intensive. Honestly, at this point, I could have just left the emulator at that, but I wanted to hear that beautiful 8-bit music in my ears. Fortunately, the audio processing unit of the NES, the APU, isn't tightly coupled with the system, and as far as I know, most games, if not all, will work perfectly fine without emulating the APU. Usually, the best way to accurately emulate the system is to emulate each chip one by one sequentially. However, since the APU isn't tightly coupled with the system, and we're doing all the emulation work in one CPU core, I had the idea of offloading the emulation to the extra 3 core in the ESP32. Additionally, we can also offload input polling. This will allow us to parallelize the emulation work and will result in basically zero slowdown for the emulation. Now there's only one thing left. For the cherry on top, I've been using the default OFAST optimization flag for the compiler, but we can add some more optimization flags to really squeeze out every bit of performance we can get. And that's all the big optimizations I've made on the emulator. Everything else is just minor code and structure optimizations to make it easier for the compiler to optimize the code. Up until now, the hardware I've been using has been on this messy proto board. It works, technically, but where's the fun in that? If this was going to be a real, fully fledged handheld, it needed a proper PCB. The problem? I had zero knowledge. I had never designed one before. So, I started from zero and started learning about schematics and PCB design, and it was very confusing. Now, if I wanted this to work, I had to take this seriously. I started by creating schematic symbols for each module. The ESP32, the display, buttons, and power supply, and then wiring everything together. The first version looked like absolute chaos with wires crossing everywhere and was very hard to read. So I went back and cleaned it up, and here's the result. Once the schematic was done, I moved on to the PCB layout. Because I'm a broke college student, I went with a 2-layer PCB to keep down costs. But that meant I had to be careful with electromagnetic interference, or EMI, and noise. Why is that important? Well, have you ever had a speaker do this? This is electrical noise that the speaker is converting to sound. This can cause signal degradation, data errors, unreliable system operation, and interference with other devices. I started laying out the parts and routing the pins as best as I could, doing my best to avoid jumping traces through the bottom layer. I also made sure that power traces are thicker than signal traces, as they carry more current. Once that was done, I filled the top and bottom layer with a copper pour acting as ground. A copper pour is essentially areas on the PCB that are filled with copper to fill in unused space, which are typically connected to ground. Copper ground pours provide a variety of benefits, the most important of which are improving signal integrity, reducing EMI and noise, and, as an added bonus, better thermal management, as these large areas of copper essentially act as heat sinks, helping spread heat away from hot components. What's more, these copper pours add little to no cost in fabrication, as PCBs start out as a sheet full of copper anyway, so there's little reason to not use them in most circumstances. It's best practice to maintain a solid, uninterrupted ground layer to provide a clean return path for signals, which prevents noise. The bottom layer is usually dedicated to this solid ground layer in 2-layer PCBs. This means that using the bottom layer for routing cuts and breaks this plane, increasing EMI and noise. So, it's best to avoid routing on the bottom layer and routing everything on the top layer. This is also why I avoided jumping traces through the bottom layer as best I could. Unfortunately, I did have to jump a couple of traces here and there, but we'll have to compromise on that. Once the layout was done, I double-checked connections and ran design rule check, and all that was left to do was to get the boards printed. Luckily, this video is sponsored by NextPCB. NextPCB manufactures high-quality PCBs with fast production times and offers assembly services so you can take your design files and turn them into real professionally made boards. Placing an order is simple. Upload your Gerber files, choose your board specifications like PCB thickness, number of layers, and solder mask color, and hit submit. If you're thinking about or working on your own hardware project and you want to turn it into something real, NextPCB can help you bring your ideas to life. Thanks to NextPCB for being my first ever sponsor and supporting this project. While I was designing the PCB for the module-based version, I had another idea. Since NextPCB was sponsoring this project, and I was already learning PCB design from scratch, why stop at just connecting modules together? Why not design a version using actual integrated circuits instead of pre-built modules? Using ICs would also allow for a smaller form factor, so I decided to push it further. Little did I know what I was going to put myself through and how grueling it would be. With modules, most of the hard electrical engineering is already solved for you. With ICs, you're responsible for everything: resistors, capacitors, diodes, inductors, and transistors. And for someone who has never even worked with them, let alone touched them before, this was a steep learning curve. I had to start reading datasheets for every component I had to use, several hundred pages. Trying to understand how these ICs work and the recommended layouts was grueling, but eventually I powered through and finished the design. Luckily, it wasn't all that bad. An advantage of using ICs instead of modules is that we can use better ICs compared to the ones in modules. I also added a few more features in this PCB, like a fuel gauge to monitor battery percentage, several fuses and TVS diodes for extra circuit protection, and a transistor to control the brightness of the screen through PWM. This is the final result. To be honest, I still wasn't sure if this was going to work. For this PCB, I'll be using NextPCB's assembly services. So I finalized both designs, ran DRC, double-checked them, and sent them off for fabrication. A few days later, this showed up. Seeing the PCBs I've made for the first time after all that pain felt great. These PCBs look amazing. Of course, a PCB looking good doesn't mean it works. So the next step is soldering everything on. This is where I find out whether I made working PCBs or really expensive coasters. Starting with the first PCB, I immediately realized I had made a big mistake. If you take a look at these holes and compare them with the other holes, you'll notice that they're smaller. That's when it hit me. I made the diameter of these holes exactly the same as the pin diameter, and completely forgot about manufacturing tolerances. Fortunately, if I forced the pin headers hard enough, they would go through. Continuing, I soldered the amplifier, the micro SD card reader, and the ESP32. We've got some of the main components soldered now. I say let's program the ESP32 and test it. And oh, yeah, that's right. I forgot to keep the USB port accessible to program the ESP32, another mistake that needs fixing. For now, I'll solder the ESP32 slanted a bit to give me just enough space to plug in my USB cable. Soldering the display next. I tested the ESP32 and it just gave a white screen. After a bit of thinking, I realized it's because the micro SD card reader has a pull-up resistor, and one of those pins is connected to GPIO 12, which is a bootstrapping pin that has to be low on boot. So, off it goes. After that, I turned my attentions to the buttons, and I checked the pins, and they would not go through. So, instead, I cut the pins shorter and soldered them on the surface of the pads. That's not the last of it though. The dimensions of the voltage regulator and battery charger module were wrong, so some pins weren't in the correct positions. To solve that, I bent the pins as much as I could to try and fit them through the holes. I continued soldering and testing after each module. Then, suddenly, the device stops turning on when I add the voltage regulator module. I checked the voltage regulator and it was burning hot. Immediately, I removed the power and rechecked my schematic. I took a look at the symbol I had made of the voltage regulator and compared it to the pins of it, and I realized I had reversed the power out and ground pins. I honestly can't believe I made such a rookie mistake. So I had to remove the pins and reconnect the output with the wires. And thankfully, that's all the problems. All that's left now is to solder the connector for the battery, speaker, and power switch, and to connect them. I honestly forgot to add pins for the power switch, but we can just wire it up and hot glue it to the PCB. Hot glue solves everything. Here's the moment of truth. I've already programmed the ESP32 behind the scenes. Let's see if it works. And it works. Alright, really quick, let's check the second PCB. This was already assembled by NextPCB, so we just have to see if it works first try. I powered the PCB and the LED turns on, but of course, it didn't show up on my computer. At this point, I was really worried that I messed up the whole PCB. I started checking everything with my multimeter. Is the power supply fine? Is the voltage converter outputting 3.3 volts? Are the chips fried? Eventually, after a lot of troubleshooting, I checked the chip that allows for communication with the ESP32. And would you look at that? The ground pin was somehow at 3.3 volts. Checking the schematic, the ground pin and power pin were indeed connected. I feel ashamed that this slipped by me. Thankfully, we can fix this pretty easily. I cut the traces for the ground and power pin with a cutter, and I manually soldered enameled copper to connect the pins to the correct place. I tested the PCB and it shows up. I tried to upload the software, but it kept failing. At this point, I already had a suspicion of what was causing it. Just like with the first PCB, I also had to remove a pull-up resistor for GPIO12. I also had to cut some traces for the amplifier and resolder because I had the capacitor connected wrongly. Finally, it works. All that's left to do now is to 3D print a case for the system to complete the handheld. Now, I don't know about you, but I love the idea of transparent tech. It's sad that the trend of transparent tech back in the 90s has gone. Not that I was even alive to experience it, but being able to see the electronics inside is just so cool. So I decided to get a transparent resin print of the case. I went ahead and modeled the snap fit cases for both PCBs. And yes, this is also my first time CAD modeling. I quickly learned and practiced how to CAD model and did the cases. Now, I'd also love to talk about this, but this video is getting a bit too long. And the case is pretty simple anyway. If you want to build your own, everything you need is in the description in the GitHub repository. I've also open sourced all of my schematics and PCB designs. The build itself is pretty straightforward. You just need to connect the components, then flash the firmware directly from your browser using a web flasher. No software install or compiling needed. So I got the cases printed, assembled the handheld, and here's the final results. When I started Animoya ESP32, I didn't think it would come together the way it did. There were lots of moments where I wasn't sure if I could ever get the emulator to a playable state. But looking at the finished product and seeing actual people liking and using it, I'm genuinely proud of how it turned out. I believe I really outdid myself with this project, as this has been my most polished project to date. If you like this video and what I do, like, subscribe, and let me know what you think in the comments. See you in the next video. Thanks for watching.